Now is the time to talk about the overview of the history and usage of test-driven development. Many people claim that TDD is just an ivory tower, a thing that was invented by some academic. At work, when I first started raising the topic, one of my colleagues said, "This is just a theory, right? No one has actually ever used it in real life." That's not quite true. The very first known usage of test-driven development in a computer environment was way back in 1944 by a group of female programmers called the Top Secret Rosies in the USA. The algorithms they were testing using test-driven development were all about the optimal place to drop the bomb on the enemy. In more recent times, in 2003, an American software engineer called Kent Beck is credited with discovering test-driven development whilst he was working on a payroll project for Chrysler. He himself says he doesn't invent it, he rediscovered it. In any event, it was so successful, he made a lot of friends and fans in a big hurry, including a gentleman called Robert Martin, author of Clean Code. He's known as Uncle Bob. You'll hear a lot about him in this course. They, Uncle Bob, Kent Beck and others, are the authors of the Agile Manifesto, and you'll hear buzzwords like agile programming, extreme programming, which aren't all to do with TDD, but TDD plays a big role. Other languages adopted TDD almost at once, along with frameworks. ABAP wasn't that far behind the 8 ball, as it became available in the first version of ECC 6 in 2006. So that's not too bad. Companies like Amazon, they put a change into production, on average every 0.59 seconds. Compare this to the traditional SAP release cycle for your custom code. That could be twice yearly or quarterly. Even then, the testing effort is enormous and things usually go horribly wrong, requiring emergency fixes and the like. How come they, the Amazons of the world, can change their production system all the time in a manner, and we can't? The answer is, they can be virtually 100% sure that any new change will not break existing functionality. This is achieved using automated regression testing. It covers 100% of their existing code base. This is not all down to TDD, but TDD plays an important part. The whole change process involves something called DevOps. This term means a different thing to every single person you ask, but the general idea is that after you change something, change your code, the changed code must go through a pipeline of checks before moving from development to test, say. The code is not moved until all of those checks have been passed. One of those checks involves automated unit tests. Therefore, TDD is not feasible unless you have a framework to run all your tests in an automated fashion. Luckily, virtually every programming language enables this. Most languages support an automated unit testing framework. It's virtually the same in every language. The generic term for such a framework is called XUnit. The Java version of this is JUnit, the JavaScript version is QUnit, and in ABAP, strangely enough, it's ABAP Unit. They all work in pretty much the same way. However, opinion is divided as to whether using such a framework is a good thing. Programmers in every other language say yes. Programmers in ABAP say no. It's been 13 years since ABAP Unit was introduced to the ABAP language, and the take-up is very low. The take-up of TDD is lower still. At one point, I thought I was the only person in the world doing this. When questioned about this, everybody else does it, why don't you? A typical ABAP programmer would say, if everyone else jumped off a bridge, would you jump off it as well? I would say that if jumping off that bridge made me able to change my programs 100 times faster with 100 times less risk, then yes, that is a bridge I'm willing to jump off. Now we move on to the purpose and definition of TDD. There'll be 2 lessons in this section. The first one will be about TDD in theory, the second about TDD in ABAP. Computer programs start their life as a thing of beauty. Then they rot over time like a piece of meat left out in the sun. They become more complicated, multiple developers work on them, they're made to do things they were never originally intended for. Often, with every such change, they not only become worse, they become more business critical. In essence, they become more fragile with every change. Eventually, it's just too dangerous to even think about changing them. This is unacceptable in a world where change comes faster and faster every year. We need to turn this on its head and have programs that get better every time you change them. The book Anti-Fragile by Nassim Nicholas Taleb was not about software at all. It was about things that improve under stress. Example, a biological organism like a human who does bodybuilding, or political structures. The concept, however, does actually apply to software. If you consider that each change is something that places stress on the program. If something is fragile, when it undergoes stress, in the best case, it stays the same. It gets worse in the worst case. If something is robust, it stays the same regardless. If something is anti-fragile, it stays the same in the worst case and gets better in the best case. We want our programs to get better with every change. This can be done, and TDD is a great way of achieving this. In order to solve a problem, we need to know what causes the problem. So what is it that causes programs to rot? It's legacy code. If you ask 10 different people what legacy code is, you'll most likely get 10 different answers. There is an official definition, however. What legacy code is not, however, is the code you had before you went onto SAP. People talk about the legacy system, but that's not what we're talking about here. Also, it's not procedural programming. Legacy code can be written in any programming style, in any language. So what is legacy code? The answer is very simple. Legacy code is code that does not have automated unit tests. As a result, a very large proportion of ABAP code that's being written this very second all around the world qualifies as legacy code. Hence, the programs being written will suffer all the problems of ever-increasing fragility. The quote from Michael Feathers speaks for itself. I'll give you a few seconds to read it. To him, Having tests in your program is so important, everything else just pales by comparison. If you have automated tests, your code cannot possibly get worse as time goes by. It can only get better. So, how do you write programs where everything gets automatically tested? Traditionally, you do the tests manually after you have written the code. Now you have to change the way you've always programmed and do everything backwards. With TDD, you write the test first. This is known as a so-called red phase. Then you write just enough code to make that test pass, the green phase. Then you improve the quality of the code you've just written, the blue phase. The whole approach forces you to write solid programs. A program written from scratch in this way, by definition, has 100% of its code covered by tests. This brings us to the end of this lesson. Now that you understand the theory, in the next lesson, we'll see how this is enabled in the ABAP language. There are three things that enable test-driven development in ABAP, the first of which is ABAP Unit. In ABAP programs, you can include test classes to store your unit tests. In global classes, there's a special section for this. In executable programs, function module pools, you generally have a separate include to store the test code. A test class contains a series of test methods which all get executed during a unit test run. A test method will verify the correctness of the behavior of one or more routines in the production code. These classes are defined as for testing. They travel, i.e. get transported, along with the code they test, but they cannot be run in production. Test classes do not even compile in production. Hence, they have no adverse performance impact on the underlying program. From either SE80 or ABAP in Eclipse, also known as ADT, you can execute all of the unit tests in regard to the program being displayed at the click of a button, just like the extended program check. There's also an option to show what percentage of the production code is actually currently covered by unit tests. You can also run unit tests for all the objects in a development package at once. Naturally, you can create unit tests in both SE80 and ADT, but doing so in ABAP in Eclipse is much, much easier. 99% of the time, test classes are local classes. It's possible to create a global test class, and this is in fact needed to test things like CDS views, but generally, a test class will be a local class within the program being tested. This is to ensure the test gets transported alongside the actual production code. In procedural programming, you'll be used to double-clicking on a call to a form routine which does not yet exist. The system will ask you, do you want to automatically create that new form routine? And bingo, it's created. For local classes, you get no such prompt in SE80. You just get an error. In ADT, however, you can use a quick fix to create an empty skeleton for both the definition and implementation of the not yet created method, plus the signature of the created definition will be correctly typed based on the variables you're passing in, which is one up on the way SE80 creates empty form routines. This way, not only is the test code created much, much faster, but you can also, and this is more important, you can truly write your programs in a test-first manner. ABAP does have a mechanism to generate test classes and methods based on existing code that hasn't got any tests, but that's the wrong way around. We want to test first. Like it or not, ABAP in Eclipse, or something similar like Visual Studio, is the future of how you're going to develop ABAP code. As an example, it's mandatory when writing ABAP in the cloud. Since you're going to have to use it, you might as well take this opportunity to get used to it. Over the years, SAP has added many tools to support test-driven development. Unit tests require test doubles to simulate things like external interfaces, database access, so on and so on. Creating test doubles can be quite time-consuming. So other programming languages, like Java, developed frameworks to make this process a lot easier. So did SAP. There's a general framework to create test double for any type of class, and specific frameworks to create test doubles for SQL statements and CDS views. ABAP Unit is a generic unit testing tool to test ABAP code, but sometimes ABAP code is wrapped inside other SAP technologies. So those technologies need testing as well. Due to this requirement, SAP has developed various application-specific test tools for such technologies as WebDimbro ABAP, the Business Object Processing Framework, BOPF, and the Business Rules Framework, BRF+, and so on and so on. It's outside the scope of this course, but much as we might not like it, SAP programming these days is not just confined to ABAP. The user interface is more and more being created using UI5, which has JavaScript as a programming language. JavaScript has a big bunch of unit testing frameworks, all with funny names like OPA and Gherkin. Luckily, SAP has changed the Web IDE, so it's got fantastic documentation on all these strange things and how to use them. And moreover, there's little buttons where you can press and it would auto-generate empty skeletons of unit test classes in JavaScript to help you on your way. That's the end of this section, which has been more theoretical. In the next section, we'll go on to the actual mechanics of how you do test-driven development in ABAP. We are now in section 2, which is all about the mechanics of doing test-driven development in ABAP. And the first lesson is all about how you go about designing testable code. Traditionally, in ABAP, routines do lots of things at once, far too many in fact. This is because it's so easy in ABAP. You want to read the database, shove in a select statement. If you want to ask the user something, do a pop-up to confirm, etc. This is all fine, but it is easy, but it makes the code impossible to test. The reason being is you need a real database. If you're doing a direct select statement, you need a real user. If you're doing pop-up to confirm, in such cases, only manual testing is possible. In order for automated testing, you need to split up the responsibilities. You need a special class for each of these responsibilities, which are also called dependencies, by the way. You need a class for database access, a class for dealing with the user, a class for dealing with an external interface, and so on for every dependency which you identify. During a unit test, those classes that deal with database access or any other dependency get replaced by a so-called test double. When the code runs in production, the real class is used. In both cases, the production code doesn't know if it's got a real class or a test double, and it doesn't matter, it doesn't need to know, because the behavior will be the same regardless of what is being tested, i.e. the business logic. Let's have a look at two sorts of code. First of all, going to look at some code which is not testable in the slightest. The reason this code is not testable is because if you look not so closely, you'll see it's got several select statements inside it. So it needs a database in order for the test to run. And normally your tests are running in development, and quite likely there is no data in the database. And even if there were, it would keep changing, and that would keep altering the results of the test, thus making the test meaningless. What we need to do instead is have a so-called factory, and that factory will give us an instance of the class that reads the database. Then instead of doing a direct select statement, we do a method call to the database access class to get the results. As I said, in production, that will read the actual database. In a unit test, it will return some sort of hard-coded value. So the result of the test will always be the same. Here we have an example of a helper class. In this case, persistency layer, which is what I call a database access class. You'll note here, it's friends with the factory, and it's got create private, which means it cannot be directly created. You have to get it through the factory. So this means anything using this helper class is by definition testable. This is the helper class. This is the factory itself. It's friends with the injector. And what that means is the injector can change it, i.e. inject values into it, change the values, the private values in the factory. This is needed. So during a run of a unit test, the test double can get injected to the factory, so it will end up in the production code. This is the injector, as you can see at the start, because of all the extra words in the definition. It's a test class as defined for testing. This means it cannot compile in production. Its only use in life is during a unit test. You'll notice in these example classes that everything is defined with reference to an interface. We need to talk a little bit about interfaces at this point. As we have seen, the helper classes are all defined via an interface. An interface is a really, really difficult concept to get your head round. You might have heard me say that the testable code is solid. The D in solid stands for the dependency inversion principle, which is a mouthful. What it says is that classes should depend on interfaces rather than concrete classes where possible, i.e. everything that's public, everything that other classes use needs to be defined by an interface. You need an example. When people first see an interface, they think this is odd. It looks like a class, but there's no code. What's going on here? An interface is a sort of contract saying what functionality is available. The example I give is an accountant. You can see him in the slide. He's got several interfaces. One of them is accountancy interface. In his day job, the company only knows what he can do as an accountant. They don't know anything else about him. They don't care what else he can do. They just need him to be an accountant. At night, he's a secret agent. The spy company only knows about his secret agent's abilities. He only exposes his secret agent interface to them. You could have someone who was both an accountant and a spy and also a circus clown. On the weekend, when he does his show in the circus, he only exposes the clown interface to the circus. The circus only knows about the clown interface. They only care about this. This is the principle. And it's good programming that interfaces should be used for all public methods. This technically enables test doubles to be created. They don't work properly unless you expose the public class by an interface. And that's good programming anyway. It's best practice. It's solid, as I've said. That's best practice. I'd now like to diverge and talk about worst practice. How not to make code. SAP has come up with the horrible, horrible concept called test seams. In this, you change the production code by wrapping a so-called test seam around the code you want to replace during the test. I will show you how this looks like in code. On the left, we have some production code. And in this example, we want to change the authority check. As you can see, in the production code around the authority check, we have a test seam just before it and an end test seam just after it. On the right is a unit test. It does a so-called test injection, which replaces the real code with some hard-coded, in this case, setting the SY subrec to 0 to simulate the authority check passing. That's all great, and it works, but don't do it. It's horrible. It's an abomination. There's two reasons for that. First of all, it's just as much effort as replacing the real code with a test double, so I can't see the benefit. It doesn't make life easier for you. But much more importantly, it breaks every single rule in the book. The most important one being that production code should not know it's being tested. A real-life example I can give of this is the car company Volkswagen. It had set up its cars using the onboard software that when they were being tested, one level of emissions came out, and when they were driving for real, a much, much higher level of emissions came out. This is a real-life example of test seams. The code behaves completely differently, business logic-wise, in production than it does during a test, thus making it meaningless. And it didn't do Volkswagen any favors because they caught out and had to pay a load and load of fines. So don't do that. Do a factory test lookup method instead. It's known as dependency lookup, where you use a factory and injector, and it's great. It's recommended by SAP. It's simple, works like a charm. Now we know how to make code testable. That brings us to the end of this lesson. And in the next lesson, we can move on into turning requirements into tests. In order to demonstrate how to turn a requirement into a test inside SAP, we are going to take a realistic business requirement and then look at how to design and build an application to deal with that requirement in a TDD manner. In this example, which will be used throughout the course, the planet Earth has been invaded by space aliens known as short dumps who come from the planet Runtime Error. You've probably encountered them yourself. They look a lot like giant mice and seem pretty much indestructible. Luckily, the Human Resistance Movement has invented a new sort of bomb called a teeth bomb, which looks a lot like a huge pair of false teeth, and when thrown at an alien, latches onto it and eats it whole. Your job is to design an application that a resistance fighter can access on their smartphone, which reads a database table to see how many aliens are in the vicinity and then a configuration table to see how many bombs it takes to eat a particular type of alien. Then it calculates the required number of bombs needed. Too few bombs, and the aliens will survive. Too many, and a scarce resource is being wasted. The front end, or view, will be in UI5, but let's not bother about that in this course. We're focusing on the back-end logic, the model, which resides in the SAP ERP system, in ABAP, naturally. Now you know the example scenario that's going to be used in this course. Some might say it's not as realistic as all that, but you should see some of the actual requirements I've been given in real life. Leaving that aside, next, we'll look at how to turn the requirements listed in this functional specification into tests inside our programs. Functional specifications can be overwhelming. The level of quality of specifications varies dramatically, and of course, naturally, the specifications keep changing. On the right-hand side, you'll see an actual specification that I got in real life, written on the back of an envelope. I wrote that myself, based on the contents of a video meeting when it became clear I was not going to get anything formal. Yet I had to write the program anyway, and in a hurry. Sometimes, of course, you can get an incredibly detailed specification, if you're lucky, but most of them fall into the post-it note category. Many times people have said to me that you cannot possibly use TDD for a particular program because the specifications are too vague. I say, in such situations, you're pretty much making the requirements up anyway. So, frame those requirements, which you've made up yourself, as a set of tests. Then, later on, when you show the tests back to the business analyst, they'll tell you they're wrong, which is good because then they'll give you more precise requirements. Requirements always change. It's only natural. The tests should change with those changing requirements at the same time as the code. A good way of breaking down a specification is to turn it into a so-called user story. They're always in the format as a stroke, I need, stroke, so I can. Good programmers should always be able to grasp the business requirements, to know why we're writing the program we're writing. If you know this information, rather than blindly following a set of instructions, the end result, i.e. your program, will come out 1,000,000 times better. In our example, as we have said, the Earth is being invaded. The business requirement is to drive the aliens out. Thus, the example user story is, as a resistance fighter, I need to calculate the number of bombs I need so I can kill the invading aliens. Neatly matches our format here. No matter how complex the end requirements are, you can start splitting them up into smaller chunks along the lines of, in order to do A, I need to do B first. And in order to do B, I need to do C first, etc., etc., etc. And so on until you have a small enough task that you can code, by which I mean write a test for. The end result of all this is your tests become a set of executable specifications, by which I mean the tests say what the program is supposed to do and prove that it does or does not do what it claims to do. Since the tests have to change when the code changes, they change, in fact, just before the code changes. They're always up to date, and they live with the program being tested. So the best form of documentation it is possible to have. They beat a test on a piece of paper, hands down. But let's just say a test was on a piece of paper. What would you expect to see in a test script if it were written on a piece of paper instead of being coded? I want to start this slide by talking about behavior-driven development. It's a concept invented by an American software engineer called Dan North. It concerns the naming and the contents of test methods. The name of a test method should be a list of the required behavior of it, where it is the application you are creating. These behaviors come from the user stories, which you just created by breaking up the functional requirements document. Within each test method, we split it down into 3 different sections again. I usually have one method for each, in a given, when, then format. This format is often described as acceptance criteria. The given method sets up test data to be used. The when method is a single call to the production code being tested, one method of the class under test. The then method is one, possibly more, usually one, assertion. An assertion saying the result is what I expected, or it is not what I expected. The business analyst, and you can see one here, they should be able to read the code. You probably noticed business analysts sneak into your code and have a look at it. They should be able to read the test code and have a look at it and say, aha, that is exactly the specification I wrote, or maybe not, and then they'll complain. At this point, we have a business requirement, and we know what to do with a test method. So it's time to start actually coding, starting with a test. A test class is defined with addition for testing. We mentioned that earlier. We also mentioned test class travels with the code it is testing. When you're defining a test class, you have a whole bunch of options. In SE24, they're drop-downs. In Eclipse, you write them manually. They're a bit pointless in my mind. They have things like risk levels, which should always be harmless, and duration, which should always be short. This is because the concept of a unit test that isn't harmless seems bonkers to me. Of course a test should be harmless. And the duration should be short, seconds at most, because you're going to be running it all the time. You're going to be running the unit tests again and again and again every time you make a change, so of course it should be short. There's no reason at all for a unit test to take a long time. After all, it doesn't read the real database, it just does calculations, which for a computer is lightning fast. There's a setup method in a test class which is called before every single test method. This sets up the test doubles, for example, and clears any global variables. It's making sure that it starts off, it being the test method, on a clean slate. The reason being that tests should not be able to influence each other, i.e. the result of one test should not be able to influence the result of another test. SAP says that the order the test methods are called in is random. I'm not 100% convinced about this, but we might have to act as if they are, just in case they are. During a test run, all the test methods are executed, and it's probably best if we have a look at the code for such methods. First off, let's have a look at a test class definition. At the start, I say which interfaces I'm going to use for my test doubles. Then I say the most important point, the class under test, which is my alien bomb model in this case. In the methods, there's a setup method, which is called before every test method, then a list of test methods, and the naming conventions is things that it should do, where it is the application that we're testing. We've only got 30 characters to play with here, so I've got like it should followed by dots, take me up to 30 to make sure I don't go over. I have a list of my 4 testing methods, which are the testing methods they're going to get called, and then some helper methods to make my test methods look like plain English. The setup method, first of all, I create any test doubles I need, then I inject them into the factory, which the class under test is going to use because it calls production code which uses the factory. I create the class under test and clear the global variables. Lastly, here is an example of one of my test methods in the given, when, then format. As mentioned, the given sets up the data to be used. The when is a call to the production code. And the then is the assertion being that the data is correct. This brings us to the end of this lesson. We have the basic structure of the test class in place, and now we can move on to the TDD cycle, which is called the red, green, blue cycle. And we'll see that in the next lesson. We are now in the red stroke green stroke blue TDD cycle. You start with a new requirement, often called a user story. In our example, the requirement is, as a resistance fighter, I need to calculate the number of bombs so I can kill the invading aliens. This is something it should do, where it is the application being developed. This requirement becomes a test method. That is, a method in the test class defined with for testing at the end. Ideally, the name of the test method should be exactly the same as the user requirement, but in ABAP, we have a 30-character limit, unlike in some languages like Java. So I tend to use the middle bit to name the test method. In this case, calculate number of bombs needed. Sometimes I put comments on the end if it's not clear enough. Because remember, some of the business analysts are going to be looking at this and they need to recognize their requirement. In that test method definition, you have the SOAK acceptance criteria, which is the given, when, then structure. The given sets up one or more pieces of data which are going to be used during the test. The when part is a call to the production code being tested. And the then part is a so-called assertion to prove that the code actually does what is required. The good thing about using ABAP in Eclipse for this is it does the hard yards for you. As a good example, you write the name of a new test method, click on it, do a quick fix, and it auto-generates the implementation for you. It's the same with the given, when, and then methods. Let's see what that looks like inside ABAP in Eclipse. Here we are inside ABAP in Eclipse. As you can see, I've got my test method, which is to calculate the number of bombs needed. And at this point, I have not generated the given method saying given customizing. I've written the calls to the methods, but they don't actually exist as yet. Notice I've tried to make everything look as much like English as possible. I've used constants for the values. Instead of the number 3 bombs. It's silly, but the point is the whole thing has to read as much like plain English as possible so the business analyst can recognize it as a requirement that they gave you. The other important things, the constants are typed as variables. We'll see why that's important in a second. So I'm getting an error here because the method definition and implementation does not exist. I've just written a call to a non-existent method. In ABAP in Eclipse, I can press Control and F1 to a quick fix, and it says, oh, this method does not exist. Do you want to create it? So, yes, I do. Click, click. Now, it's going to create the method definition and implementation for me. Note, it's going to create a signature, and it's picked up from because I'm using variables, the correct data elements. I finish. Great. Because it's a small screen, I can see straight away it's created the definition up here. So the definition's been created for me, and by pressing F3, I can go into the implementation there, and it's given me a blank skeleton implementation. It's just a question of repeating that process for each of the other methods in the test method. This is the benefit of ABAP in Eclipse. You can't do this in SE80 because it's local methods. Many years before I'd even heard of the concept of unit testing, my organization had test scripts written on pieces of paper with the expected inputs and the expected outputs. A unit test is just like that, except it lives inside the system along with the code. So, of course, it's always up to date. In the then method, you say what the expected output is. This is test-driven development, so we always work backwards. So we're starting from the end, as in the expected results. That's why we code the then method first. This is done by means of an assertion. Some people say you can only have one assertion in a then method. I'm prepared to be flexible on this. As long as it's testing the same sort of result, then you can have more than one. I'll forgive you. Since in good programming, a method just does one thing and does it well, it's highly unlikely there's going to be a load of different unrelated results coming back. So one assertion usually does the job. Then in the given method, you set up the data that's going to be used in the test. This involves test doubles 99% of the time. It's possible to manually create local classes which are test doubles, but in this example, we're going to use the SAP recommendation and have the test double framework automatically generate the test doubles for us. As you'll see in a second, the syntax is all over the place and it's very illogical, but once you've done it once, you know what to do, no matter how silly that might be. Let's have a look at what this looks like inside SAP. Here we have the then method. As I said, everything's going backwards. We start off by saying the result should be. In the Body of the test method, in our example, it's passed in 15. And that is what we want. We want to have 15 bombs. And if it's not, the unit test is going to stop with an error. Then we code the given method, setting up the data. We've got two given methods. I'm just showing one here. And now it's a funny syntax used by the ABAP test double framework. It's all backwards. First of all, you tell it what the result is going to be, and you haven't even mentioned what method of the test double is going to be invoked. You do the result first. Very strange. Nonetheless, that's the way it works. That's the way it is. Again, you notice here, I'm trying to make it all read in English. It does sound a bit like Yoda, everything being backwards. Like, in City London, of type Eater, there are 5. That's the way he speaks. That's the way I write my unit test as well. And the second part of the test double framework, you say what method is going to be called, which will give the result you've just said. It's, again, the syntax is very odd, but I've hidden it away here inside a given method. So a business analyst, for example, doesn't have to see it. They don't need to know you're using a test double framework, because that's a technical detail completely unrelated to the business. These test doubles are created at the start of every test method by the setup method. As you can see here, we're creating a test double, and it needs an interface. Test doubles need to be defined relating to an interface. In this case, I've got my persistency layer interface. I don't like putting hard coding values into method calls, so I always use a variable or a constant. And that's how it looks. We have now reached the most important part of the test-driven development cycle, though it might not seem like it at the start. At this point, you've replicated the test script. You say what the inputs should be and what the expected result should be. So the test code covers the what, but not the how, and that is as it should be. The given and then parts of the test method are aimed at the end user, or at least business analyst. They're end user facing. The when part is a black box, as this is solely the province of the developer, i.e. you. Why is this the most important part of the cycle? It's because it is vital that you do not write even one letter of production code before you have a failing test. If you don't have a failing test, then you don't have a benchmark. You've got no way at all of gauging when you've written enough code to get the test to pass. So we will run the test now. It will obviously fail because we haven't written any production code yet. Let's see this in SAP. Here I am in Eclipse looking at my global class, my alien model class. I'm now going to run the unit tests. And I expect it to fail because there's no production code yet. So I choose Run As, ABAP Unit Test. There's a shortcut as well, which is what you'll probably usually use. I run it, and we have a failure down the bottom. The icons are really, really small down here, but here we say one of one tests has failed. Then it shows what the test is. Notice the incredibly small length of time it takes to run a unit test. This is vital. And then over here, we've got the details of the test. We expected 15 bombs to be calculated. In reality, 0 bombs were calculated, which is not surprising, considering there's no production code as yet. That's good. We've got a failing test. We've got a benchmark. Now we can move on to the next phase, the green phase, where we start writing the production code. You have now reached the green phase. The given and then methods are complete, so now you turn to coding the when method. The when method is generally filled with only one line of code, and that line is a call to the method being tested. In this case, in our alien example, the method will take in a value, the city, read from the database twice, do a calculation and return a result. The test code doesn't need to know these how details, only the signature, which is export a city and get the required number of teeth bombs back as a result. Naturally, when you code this method, i.e. a call to the production code, you'll get a syntax error for the very obvious reason the production code method doesn't even exist as yet. Now this is good. According to the theory of test-driven development, a syntax error in a test class, it counts as a failing test and so needs to be corrected. Great. Happily for us, Eclipse works with us here because we've coded a method that doesn't exist, a call to a method that doesn't exist, and using a quick fix, we can automatically generate the method in the class under test. The test still won't pass at this point because the method being tested is empty, but it's a next step along our journey. We'll have a quick look at this in SAP. We are now inside ABAP in Eclipse, and I'm in the when method. It's got a syntax error at the moment because the production code, the method, calculate bombs needed, does not yet exist. In the usual way, I'm going to use a quick fix in order to create that production method. I press Control and 1. It says, oh, let's create the method calculate bombs needed. Once again, it's clever enough to correctly type the variables. I press Finish. It's got a blank implementation and a definition. And this is in the class under test. So we've written the test first to a call that doesn't exist and then generated that code. Once again, this is test first, test-driven development. At this point, our test is still failing, which is not surprising, because although we have an implementation in the class under test for the method being tested, it is blank. So of course the test fails. At this point in the green phase, you write the absolute minimum code needed to get the test to pass. This is elegance. The definition of elegant is the simplest thing that correctly does the job at hand. That's what we're aiming for. So rather than writing reams and reams of code and hoping for the best, which is how we've always done it, the idea is to write your production code in a series of small steps. The idea of test-driven development and this cycle we are in is you'll be guided to the next step. For example, the last error message said the method in the class under test did not exist. So the obvious step was to create it, which is what we did. It's important when you're actually writing the production code that all the dependencies must be accessed by a helper class. That is, there must be no direct select statements to the database, no calls to a pop-up to confirm to get user input. All such calls must be wrapped in a helper object, otherwise you just cannot do automated unit testing. Now here's a concept that's going to blow your mind. Robert Martin, Uncle Bob suggests that if the very first test requires the result to be 80, for example, then just say result equals 80, without any calculations at all. That sounds crazy. It sounds like lunacy. It is, of course, as specific as you can possibly get. The idea behind this strange concept is that the first test will pass, of course, but as soon as you have a second test with different inputs, the second test will obviously not pass, so you have to change the code so both tests pass. The idea is, as a test becomes more specific, the code becomes more generic. This is often called the inventor's paradox, and that is that solving a complicated problem is easier than solving a specific one. Leaving that theory aside, let's pop back into Eclipse to see what the finished coding would look like. Here we have the coding of the production code. The idea is to keep writing small pieces of code until the test pass. As you can see here, we're using the factory to get the persistency layer helper class. In production, the real class will be used. In a test, the test double will be used. If you just code the calls to the database tables, nothing will happen. You need the calculation. So write one line of code at a time until you get to the stage where everything passes. You might be wondering at this point, how can it actually pass if the real database access classes are still empty, which they are? The answer is that's not what we're actually testing here. We're testing the business logic. In fact, in releases before 7.522, you cannot test database access class. In higher releases, you can use the OSQL framework, which can unit test SQL statements. And those unit tests would live within a test class, which is attached to the global database access class. To recap, you add small bits of code, a little bit at a time, until you get to the stage where the test passes. We've got to the passing stage, hence the name green phase, because it passes. If you run the test in SE80, all you'll get is a little blue line at the bottom of the screen saying X test methods have run, X test classes have run, no errors. Which is not really good. You'd like it more in your face. In Eclipse, however, it is in your face. It will tell you how many have run and detail the results. We'll have a quick look at running it in Eclipse, just so you can see. Here we are again, inside the method being tested. This time I'm going to run the unit test. If I just want to run the unit tests by itself, it's Control-Shift F10, but I want to run it with coverage as well. So it's Control-Shift F11. Here we go. Test run. Should take very little time. It tells you how long it takes, which is 0.01 seconds. That's fast enough for me. And you can see that we've only got one test and it passed. Now you might have noticed these lines have gone green. That's because we're testing with coverage. And when you test with coverage, all the production code that's covered by unit tests goes green, and any lines of code in the production code that aren't covered go red. You also have a little tree diagram showing what percentage of statements are covered by the unit tests. Now you always need to aim for 100%, though in reality, that's usually quite impossible. Though it can guide you on creating extra unit tests, because if something isn't covered, maybe you need a test to cover that situation. In any event, we've got to the stage where the test passed, so we're at the end of the green phase. That means it is time to move on to the blue phase. Let's talk about the blue phase as a concept. What problem is a blue phase solving? As you know, programmers are always under tremendous pressure to get working code out of the door just as fast as they can before the competition do. The logic is it doesn't matter how good the code is. If it's delayed by 6 months, the company goes out of business. And that's a bad thing. It doesn't matter how good the code was because no one ever got to use it. Conversely, this leads to poorly written code that crashes all the time and the company goes out of business anyway, so you can't win. The natural result of all this is a frantic rush to get something working as fast as possible using all sorts of dirty hacks and caring nothing about how stable or well written the code is. You end up with 100% of your code not being as good as it could be, and hence very difficult to understand, and hence very, very difficult to change. Rushing and doing dirty hacks is human nature, so you might as well work with it rather than fighting against it. As a result, the red and green phases of TDD replicate this situation. Just do whatever you can think of as fast as you possibly can to get the test passing. This is in many ways business as usual. The difference is with traditional development, you never improve the code after the event, leaving it in a suboptimal state forever because A, there are other things you've got to do, and B, you're scared if you go back later on and improve things, you'll break something. With test-driven development, this problem is solved by incorporating the blue phase right into the test-driven development cycle. Let us see how this admittedly abstract concept can be brought to reality in the ABAP language. Test-driven development is not just about correctness, but also the quality of the code. American software engineer Kent Beck once said, "Make it work, make it right, make it fast." In the red phase, and what it was, it being the business requirement. In the green phase, you made it work, ensuring the correct behavior. In the blue phase, you can make it good. As it turns out, even to get to this point, the code is forced to be better than your average bear because testable code is good code. Writing testable code forces you into a good design. It forces you to follow solid principles. So testable code is better code, even if you never test it. It's crazy, but it's true. In the blue phase, you can make the code right. This is a good time to run the ABAP Test Cockpit, ATC, checks. These checks will identify any hacks or dubious tricks that you used to get the code working. I would also advocate downloading the ABAP Open Checks from GitHub, and there'll be a link on the next slide to this. They're for free. You add them into your ATC check variant, and suddenly you've got a million more really good checks. Once you run the checks, keep changing the code until all the errors and warnings are gone, or you've identified them as false positives. Every single one. So many people skip this step. They all live to regret it. This is also the time to apply the clean ABAP principles. As per the style guide on GitHub, again, a link is in the next slide. This adapts Robert Martin's notice I keep talking about him. Clean Code book, the principles in that book, adapted for the ABAP language. Examples are using things like the new ABAP constructs, the latest language, like inline declarations, for example, which make the code shorter and or clearer. Identify 10 things to be improved using the ATC checks and style guides and what have you. Don't change them all at once. Do it one at a time, and after you've made each change, rerun the unit tests. Since all the tests passed before, you'll know instantly if your improvements have broken anything. Either the test you're currently working on or any prior ones. As in the make it work, make it right, make it fast, in the blue phase, you can make the code fast. How do you do this? It's a good time to run the SQL trace via transaction ST05. That might not be possible. The application as a whole has to be in a state where it can actually be run and actually read the database. Once again, this is a step many programmers miss due to time pressure, and again, they live to regret it and have to go back once the code is in production, which is far too late, to investigate why it keeps timing out. Changes here cannot be detected by rerunning this on the business model class because you've mocked the database access, so it doesn't really read the database. In higher releases of ABAP, 7.51 and up, there are frameworks to do unit tests of SQL statements and CDS views. The unit test for such things will live in your persistency layer class. And the unit test for CDS views will live in separate classes dedicated to testing that CDS view. If you're lucky enough to be on such a level, then at this point, you can improve something in the database access class and then rerun it, rerun the unit tests, and that can actually tell you if a statement will rerun. It cannot tell you if a statement will run any faster, but it will tell you if you've broken something. The way you can tell your fix has improved something is by rerunning the SQL trace. This will also, if you've forgotten to write the actual select statements in database access class, because as mentioned earlier, the business logic test will pass even if the database access class is completely blank. Let us see what this looks like in SAP. I really, really hope everything on this screen looks really familiar to you. Top left corner, we have the extended program check. Bottom left is the code inspector. In both cases, all those numbers need to be reduced to 0. A lot of people skip this, needs to be done. On the right hand side, you have this ST05 trace on an SQL statement from a custom program. It takes a little bit of getting used to understand this, but it's an exercise well worth learning, because the faster a program runs, the happier your end users are. You don't really want them running a query and then going off to get a cup of coffee an hour. It needs to be instant. They'll be happier and they'll be more productive. At the bottom are some links to the Clean ABAP guidelines, which is a style guide based on Uncle Bob Martin's Clean Code, but adapted for ABAP, and a link to the ABAP Open Checks, which is well worth downloading into your system to make the code inspector even better than it normally is. All these tools I've been talking about, ABAP Unit itself, extended program checks, and so on and so forth, they're all great. They're all wonderful. But how can you ensure that even if you personally are doing the right thing, how do you know that one of your colleagues does not sneak in whilst you're on holiday, do some sort of change and wham it into production without doing any sort of check at all. The ABAP unit regression tests can tell you if the latest change that you just made has broken anything, and the ATC can tell you if there's low-level errors in the code. That's a dynamic check and a static check. But neither of those tools are much use if no one ever runs them. Let's just say, for example, you created the most fantastic program ever written in the universe, which is 100% covered by unit tests. So in theory, it can never break. Then after 6 months, a new colleague is tasked with changing something in that application. They may not even know there's such a thing as ABAP unit. Many people don't, which is why I'm doing this course. Or they could be too busy to bother running the tests, or they can just forget. Or presume that no one ever writes unit tests. There's no unit test in this program. I won't even bother. There's a million other reasons. It goes on forever. The end result, it's an ever popular change in one area, breaking something in another area once it goes to production. Very thing writing a program in a TDD manner is supposed to prevent. The way to prevent this situation is to set up an automated batch job where you nominate a set of Z objects. Z objects that you know have unit tests. And every night, let's just say 2 a.m., something like that, the batch job runs and sends the result to someone who cares. Sending it to someone who doesn't care is a bit counterproductive. So send it to someone who cares, like yourself. That way, every morning, a list of things that need to be fixed, i.e. broken unit tests, say, appears, and then hopefully those problems get fixed whilst they're still in development. I've been using this tool in real life, and it works like a charm. That batch job with the automated email will stop, hopefully, your colleagues making changes and forgetting to run unit tests. But what if you make a change and forget to run the unit tests? Easily done. Now, you should run the changes after every single change. After all, it only takes seconds, just like a syntax check in SE80. This is called shifting testing left, or instant feedback. You cannot get more left in the development cycle than after every single code change. However, shockingly, we human beings are imperfect. I know that's difficult to believe, but sadly it's true. It's all too easy to forget to run the tests. You should run a test all the time, but some people don't, and some people never run them ever. This can happen if your mind's on other things, like a looming deadline, as in, you've got to get it ready by the end of the day or you're sacked. That can focus your mind, but it can also mean you're too busy to run the tests. As it turns out, if you develop using ABAP and Eclipse, you can force the issue. There's a lot of tools I talk about are free, a free plugin to ABAP and Eclipse called Continuous Development, where you can configure that the ABAP test cockpit, static checks, and the unit tests, even the pretty printer, run automatically every time you activate the code. And usually you activate the code after every change. That will tell you straight away if the ABAP test cockpit results fail. You'll get a little box where you can pop up and see what's wrong. If the unit tests fail, you'll get a different colored box, and that will pop up and tell you what's wrong. That's great. None of this does anything that standard SAP cannot do, but it automates the process, saving you a few button pushes which multiplied throughout the day could be a very, very large amount of button pushes. And more importantly, it prevents you from forgetting those steps. By now, hopefully, you've been convinced of the merits of TDD. However, when you mention this radical new concept to your colleagues or management, chances are they'll fight back tooth and nail. And this is what the next section is all about. Welcome to section 3. In this section, we're going to deal with the common arguments made against the whole concept of test-driven development. As I mentioned earlier, people love the status quo. People don't want to change anything. And a radical new idea like test-driven development, they'll say, oh, I don't know about that. So, in this section, we'll deal with some common arguments against the whole idea. Each lesson in this section addresses a common argument against TDD, or unit testing in general. The first argument is that no one's ever done this before, so it's too risky to try. As I mentioned in the introduction, some people think the whole TDD concept is something I made up. Now, whilst programmers in other languages have been doing this for ages, it is true that in ABAP world, virtually nobody has. And in software, it is not seen as a good thing to boldly go where nobody has gone before. I can't talk for anybody else in the ABAP world. But in this lesson, I will give little stories about what I have been doing. I only started doing TDD for real in ABAP in 2018, but I've been using the ABAP unit framework since the very first day that where I work, we upgraded to a system that was high enough release so I could actually use it. That was in 2012. So, how exactly did I go about doing this? I started by adding tests to an existing procedural program that I was 80% of the way through writing. This example was a procedural program to look up customer open items and make a proposal of how to clear them, a sort of souped-up version of transaction F-32. The test class, of course, has to be object-orientated, but the program being tested was 100% procedural. The test methods when section, all called perform statements. You can do that in local classes. Global variables, which are bad, actually help here, provided you set them up properly in the given method. As always, the requirements were very, very vague, and they kept changing. You're probably familiar with this situation. So all my unit tests could do was verify that the program was doing 100% of what I expected to do, given my best guess interpretation of the requirements. Of course, once a program is in production, suddenly the actual requirements crystallize. For example, once this program was in production, the most important requirement suddenly right out of the blue, never having been mentioned before, even once, because it was obvious to the business owner, but not to anyone else. The natural consequence of this was lots of bug reports once the program was in production. This presented an opportunity to start fixing those bugs in a TDD manner. For every actual bug I encountered in production, a new unit test was added. The bonus, of course, is hard-coded test data. I use the actual data that I got from production based on the reported bugs. This worked fantastically. Even though it was procedural, it became a rock-solid program. As I said, it's not legacy code if it's got tests, even procedural. So, for the next 6 years, I kept writing unit tests for programs, but my programs got more and more object-orientated. Until in 2018, I was finally able to live the dream. In that month, January 2018, I finally got the opportunity to demonstrate at my company that my crackpot ideas, ridiculous ideas such as object orientation, design patterns, test-driven development, actually work in real life, with the guinea pigs being our two most gigantic business-critical programs. A very big gamble, it could be said. The project I was working on was all to do with a gigantic, monolithic procedural DINPRO program and to rewrite it in a proper TDD manner. Now that program has had 20 years of development, i.e. getting added to non-stop every day for 20 years. So, as imagined, it's enormous. Knowing where to start was overwhelming. It seemed an obstacle that could not be got across. So the first step was to split the DINPRO logic into a MVC, Model View Controller, format. In a proper object-oriented fashion, the UI has no smarts at all, and the controller doesn't do very much either. All it does is decide what screen to call. So all of the business logic resides inside the model. So then it was just, as if it was simple, a case of going through every PBO stroke PAI module and every form routine that those called to see what it, the application being rewritten, was trying to achieve. Obviously there was no documentation. Why would there be? It was only the most important program in the company. The result was a very, very long list of small things that it was currently doing. You have to take this as correct behavior. You'd go mad if you thought about this too deeply. And then, for each item on that big long list, turn it into a business requirement, write a for testing method in the it should section of the test class. That starts off the red phase. Then I proceed for each business requirement with the green and blue phases. Was it easy? Was this easy? Did I find this easy to do? Was it a breeze? I'd always thought TDD was a wonderful theory based on what I read and my early experiments. So, did my opinion change after I started doing it for real, all day, every day? One thing's for sure, this is agony at the start. There's no point in sugarcoating it, it's agony. The very first red, green, blue cycle I'd ever done in my life took me 2 days. After several months, I was able to get this down and go through a TDD cycle in minutes, which is what the books say it should be. And they say, of course, you can do that straight away, but that's not really the case. Eventually, I could do this in minutes for each new requirement, but nobody could say that moving from classic, i.e. what we've always done, ABAP programming, to TDD is as easy as falling off a log. Nonetheless, my other main finding was this is worth it. This is worth it. I cannot stress this too much. Following this approach forces design change, which, as I keep stressing, is a good thing, as it makes the resulting application solid. You can literally feel the program getting better. which is a great feeling. It's a lot better adding some code and hoping for the best, which is pretty much what I used to do before the advent of ABAP Unit. I always liken this to climbing up a mountain. It's a huge effort to get to the top of the mountain, but once you're there, you're on top of the world, and you feel just that way. The difference here, and it's a good difference, is that climbing the mountain gets easier and easier each time until it's no effort at all, still with all the beneficial effects. At this point, you might have explained this whole concept to people, and the detractors will say, yes, it might work well, it being TDD. It might work well in general, but for my application, now it'll never work because of such and such. We'll talk about those arguments next. In this lesson, we're going to be examining the argument, which goes as follows. My program should be exempt from test-driven development, and indeed OO, because it's far too simple. A large number, virtually all, programs start life as an ALV report that reads data from a database, does nothing at all with it, and then displays the result to the end user. In theory, such a program needs a very small number of lines of code, especially in the higher releases of ABAP. You need a selection screen, a call to the database to fill the internal table, and then just call the class solve table using the data you've just retrieved, and Bob's your uncle. Quite often, this sort of program is described as a one-off, as in, we just need to look at some sort of data once to solve a specific problem we're having right now. Then we'll never need it again, ever. A lot of programmers would say, when you're told to write such a program, it's so simple, so few lines of code needed. Well, why bother with unit tests? What exactly is it you're testing anyway? Because the database access will be mocked, and the UI display will be mocked, and there's no business logic to test. So that seems crazy. In fact, the argument goes even further. It seems crazy to use OO programming in such a case. You'd need to split the report into several classes, a model class, which calls another class, which is a database access class, a controller, which does pretty much nothing at all, which just calls the ALV using one line of code. All these classes seem like overkill. In fact, in such a situation, even using form routines for each different operation seems like overkill. This is why, for short programs like this, a lot of programmers just stuff all the code in a big list of statements directly after start of selection. Anything else would seem to be overkill, adding a load of complexity to the program for no benefit whatsoever. So that's clear cut, is it not? Programs should not be written in a testable way. Or should they? All of the arguments I've just made are 100% true, given one basic assumption, which is the program will never change ever. After all, the specification said this is a one-off temporary program. It seems to have solved the business problem perfectly. So of course it's never going to change again. So you can forget about it. Or can you? I've been programming for 20 years, and I can tell you, without a shadow of a doubt, this assumption is false about 99.99% of the time. As soon as a program, which is initially a read-only program, as soon as that program hits production, you'll start getting requests like, "Ooh, can you make one or two fields editable so we can update the database using this?" Or, "Ooh, I think we need a few calculated fields as well." and so on, month after month, until eventually it's turned into a business-critical monster with 60,000 lines of code. I've seen this time and time again. In fact, the so-called one-off will only be used once programs are often the worst culprits. I'm going to be spending half of 2020 working on a one-off program I wrote in 2016. So what do you do? As you add more complexity to a simple program, you're going to have to refactor it from a few lines of code after start of selection into some sort of modularized structure. Given this situation, i.e. the program gets more complicated, it's almost inevitable. Why not create such programs using a template based on the MVC pattern? That stands for Model View Controller, by the way. Most famous design pattern there is. You have a model class doing any logic transformations, calculations and such. Aren't any at the start, but might as well have a place for them because they will arrive sooner or later. A view class to call the ALV and a controller to link the two. Plus an include for the test class, which you'll need sooner or later as soon as that business complicated logic starts arriving in droves, which it will. It's best to have a specialized database access class because otherwise you can't test the code and you need to make the code testable, as all code should be. I said before that the testable code is better than normal code, even if there's nothing to test, because you're forced to do a good design. On a practical level, if you've got a template, then creating a new report is really simple because you just call up a blank template and start filling it in. So it's almost as fast as writing a simple program anyway. So we have now dealt with the fallacy that some programs are too simple to be testable. In the next lesson, we'll see another object, which is the contrary one, the exact opposite argument. All the examples about TDD and unit testing that you come across on the internet, including this very course, talk about creating programs from scratch. All the code examples are 100% object-orientated, and naturally, the example programs are small. People, programmers, come away from this and say, that's all well and good, but in my job, 95% of what I do is maintaining huge, gigantic procedural programs. So this whole unit testing, test-driven development concept can't be any use to me. Then they're going to say that you can't test procedural code anyway, because it's stuffed with dependencies, database access, UI access, and the like. They're all mixed together. And as we have seen, this prevents tests. This is especially true of DINPro programs, where the business logic often lives in the UI layer. To enable a proper level of test coverage to such a monolithic program, you'd either have to rip the program to shreds and rebuild it, or create a duplicate from scratch in an object-oriented TDD manner, which admittedly I did. But either option takes a year, costs a load of money, and you don't end up with any extra functionality, just a huge risk that you break something vital. Building a business case for that, and you'll get laughed out of court. At this point, the conclusion people draw is the program is too complicated for unit testing, and so the decision is made to keep everything the same as it always has been, and the program just gets more and more fragile over time. But it doesn't have to be this way. There is a way to square the circle. I would be foolish to suggest if you've got one small bit of extra functionality to add to your monster existing procedural programming, that you should do some major surgery on it. That part of the argument is bang on right. It's far too dangerous. However, with any change at all, there's a level of risk. So the suggested approach is designed to ensure, at the very minimum, there's no more risk being taken than there would be if you made your change in the traditional way. First, do no harm, as a dog would say. The solution to this too complicated problem is, in the software industry, called an island of happiness. All your new code is written in a TDD, object-oriented way, in one or more new classes, which are then called by your existing procedural program using hooks. An example could be a new screen that asks the user something, does some calculations, and returns the result to the main program. This is not a radical new concept. Often new functionalities is added via a call to a new function module. And this, after all, is how SAP user exits work in all their various formats. The difference here is that the new code has unit tests. So you can be 100% certain that at least the new functionality is working as designed. Moreover, you're making the program more solid, as the classes have single responsibilities and can be changed independently of the calling code. A lot of changes are not about adding new functionality. They're about bug fixes or changes to the business logic. Here too, you can just take one form routine, the one you're working on, and extract the dependencies into their own classes. Then create a unit test, which tests that one form routine. Routines are supposed to be small, but in real life, especially in these monster programs, you find form routines that are thousands and thousands of lines long. That makes it much more difficult to do the island of happiness trick, but at the very minimum, you can start extracting the database calls to their own class. That's a low-risk change, and is one tiny step down the long road to making the code testable. This is no doubt extra work, especially for a minor bug. But let's see how this approach can turn an island of happiness into a continent. You've got a small change to make. You proceed, as I just said, by putting all the new code in one or more islands of happiness and changing the tiny part of the program that you had to change anyway to make it testable. Note, you don't have to build a new happy island each time. If it's just a new database access being requested, for example, you just add that as a new method to your happy database access class. You proceed to write the new code using test-driven development, and at the end you can be sure that 0.01% of the program is under test and is working as expected. And it will continue to work as expected for all time, provided the unit tests, regression tests, are run after every change. You cannot, of course, say if your new change has broken anything in the other 99% of the program. But if you're just accessing the new code via hooks, then you're fairly safe. A week later, you get another change request for the same monolithic program. You repeat the same process again. Now you've got 0.02% under test. Due to TDD, you know the new fix works, and you haven't broken the last fix. Again, you cannot be sure you've not broken the other 99.98%, but then that was always the case before, so you're no worse off. In fact, you're slightly better off, albeit marginally. The important quote on this slide is from ancient Rotronius, and he says that no one is ever satisfied with anything. This is especially true with software. So much so that I would say that if you don't get complaints or enhancement requests on a regular basis for an area of the program, that means people aren't using that area of the program. That would mean over a period of several years, you would get change requests for every single area of a program that people are actually using. If you follow the island of happiness approach, E, that means your island will get bigger and bigger, and the calling program will wither on the vine. And before you know it, your happy islands have become a continent, and 100% of the areas of the program that are used are under test. This brings us to the end of the rebuttals against technical arguments. The next lesson deals with a much more tricky subject, which is money-based arguments. By the very nature of TDD, you end up with twice as much code, at least, as you would normally. In good OO design, each method is really small, and it could be you have at least as many lines of code in a test methods as you do in the production code being tested, thus double the amount of code overall, possibly much more. When you explain this to management, they will not hear the benefits. All they'll hear is that it takes twice as long to write the same amount of code, twice the time, and time is money. The logical extrapolation of this is that you would either deliver half the amount of software you normally would in the same time, or you'd need twice the staff. Either option would have a huge financial impact. In fact, I found generally it's the extra time that'll be mentioned more than the money, because people need to get there first. In this world, everyone is under pressure to deliver software changes as fast as they possibly can. Everyone's always up against a deadline. Also in the modern world, employees in general and management in particular are often judged just on the last quarter. If they miss a target, they get sacked. Given this fact, saying to the powers that be, you have a wonderful new programming concept that will give far better code but will take twice as long, doesn't go down that well. Many programmers and software companies get around this problem by not mentioning the fact they're writing tests at all. In fact, if a software company split out the testing component on an invoice, the client company would ask them to drop that aspect on the next release, i.e. stop testing. Testing in any form is always the first thing to get cut when money's tight. This would seem an insurmountable obstacle. So, why is TDD so prevalent in the non-SAP software industry? How did I get my management to agree to it in SAP world? Here's the argument I used to justify the whole approach. Once again, I'll use a story to explain the concept. To my management, I took as an example one of our most business-critical custom programs which the company cannot live without. The first version was written in about 2 months just prior to go live in the year 2000. That's what I define as the development phase in a software lifecycle. After go live, of course, many bugs were found, which needed to be corrected. But even once the program was stable, because it was so important and impacted so many people, there were many requests for changes and enhancements. At least one such request, sometimes as many as 10 at a time, every month, every single month, for the next 20 years. It has not stopped now, and it never will. That's what I call the maintenance part of the software life cycle, i.e. the orange thing in the slide. As can be seen, when you take the long-term view, the development phase becomes a smaller and smaller piece of the pie as the years go by. TDD is intended to make this phase, the development phase, risk-free and thus cheap. So from a financial point of view, the question becomes, for a 20-year period, does doubling the cost of the development 5% phase get offset by reducing the cost of the maintenance 95% phase to next to nothing? Obviously it does. It doesn't even take 20 years. TDD starts paying for itself almost at once. That's the argument I used at my company, and it worked. But there's a better one. To use another analogy, choosing not to write a test is a bet that the extra cost of writing the test is more than the damage you'll inflict upon yourself and your organization if the functionality fails. For some industries, the cost of failure is so high, you have to take such a bet. For the same reason, you have to insure your house. In theory, the cost curve and gambling examples are killer arguments in favor of TDD. However, they require management to think outside of the short term. In real life, how many managers are allowed to think in the long term? This varies from country to country, but you have to take the worst case example and think they'll think in the short term. Luckily, even if only a short-term approach is allowed, there's another argument. When countering arguments, you need to fight fire with fire. Since the argument is that doing TDD will double the cost of development, you need to show it will in fact lower the cost of development. If you can convince a CFO of that, and most IT departments report into finance for historical reasons, suddenly you're laughing. There's been an enormous amount of study done on the so-called software bug cost curve. But if you think of it, the logic is self-evident. If a developer finds a bug whilst writing the code, it takes mere seconds to fix and thus costs almost nothing. If the bug is not found till test, then the tester has to explain to the developer what's wrong. Then the fix gets transported back to test, back to development. It may not work. This cycle may go round 3 or 4 times. So fixing that bug costs 10 to 100 times more than if it was found in development initially. If a bug's discovered by an end user in production, then there's probably some sort of business impact, often financial. Then the end user has to explain what's wrong to first level support, who have to explain it to the business analyst, who then has to explain it to the developer. Probably, as each person talks to each other person, they'll lose some information due to the so-called Chinese whispers effect. The bug fixing cycle is much, much longer and drawn out, including scheduling when the fix goes to production, people having to work on the weekends just in case. But then that fix might break something else. So the cost of fixing a bug in production is between 1,000 and 10,000 times more than if it was found in development. As might be imagined, the way to fix this situation is as obvious as the nature of the problem itself. Fixing and finding bugs early in the development process is called shifting testing left, and TDD is the ultimate embodiment of this. By the very nature of TDD, you run the regression tests after every single change, so you can be sure that the current change works as expected, and more importantly, the current change has not broken anything that currently works. Nothing's ever 100% perfect, but the idea of TDD is to catch all the bugs in the cheap as chips to fix phase. As Robert Martin put it, QA should find nothing. QA being quality assurance, i.e. the team who tests your changes in the test system. This brings us to the end of the lessons in this course. Next up is a summary of what's been covered. Now is the time to do a recap of the three main sections of this course. Traditionally, the problem with programs and programming is that programs were fragile. The more you changed them, the worse they became. And every change you made was a huge risk, as you just did not know what was going to break. Once the program got above a certain level of complexity, it became almost too risky to even think about changing it. In other programming languages, this problem was solved a long time ago by a combination of automated unit testing frameworks coupled with a test-driven development approach. Eventually, ABAP caught up with all those other languages. Some years back, SAP introduced the ABAP unit framework, which enables a true test-driven development approach when developing ABAP applications. This enables you to turn everything on its head. The more changes you make, the stronger the program is. It's become anti-fragile. In a world where the number of changes you need to make increases at an exponential rate, this is vitally important. Without such an approach, you might as well give up and go home. This is why the stellar success stories like Amazon and Google have used this approach from the get-go. Next, you heard about the exact mechanics of doing TDD in ABAP. Traditional code, procedural code, cannot have automated tests because it's full of dependencies, database access, user interaction, printing, interfaces to other programs, and so on. That code has to be changed, so all such dependencies are in dedicated classes, which can be replaced by test doubles during testing. This has got the added benefit of improving the program's design by making it more solid. It can be difficult to know where to start when building a program using TDD. The best approach is to take a functional specification, or if there is no functional specification, or a post-it note type special functional specification, take your best guess as what the proper functional specification might look like had it existed. Decompose this functional specification into small sections, each one saying one thing that it, the application, should do, e.g. calculate remaining leave balance, for example. You're focusing on the business logic here, not UI, not database logic. Each thing that it should do becomes a test method. Once you've managed that, you can get into the gut of TDD. Then, for each such requirement, you go through the TDD cycle, which has three colors. The red phase, where you put the inputs and desired outputs into a test. The green phase, where you write the actual production code to make that test pass. And lastly, the blue phase, where you polish your code until it shines. The end result is 100% high-quality code that does exactly what it should and never breaks. That sounds like utopian nonsense that can never happen in real life. But it is possible. When organizations try this being TDD, and say it doesn't work, it is always because they've taken shortcuts and don't do it properly, at least according to Microsoft. In the third section, you heard about common arguments against TDD. In ABAP world, the idea of TDD, or indeed automated tests in general, is almost unknown, despite the ABAP unit framework having existed for many, many years. Thus, people would tend to assume this is a radical new idea that's never been tested in practice. In fact, the concept has been used in anger ever since 1944 and is used in the development of every app you use on your smartphone. It has, however, not been used very much or at all in ABAP development thus far. Then you heard about arguments saying that particular types of program should be exempt from TDD. Simple programs would appear not to need tests at all at first glance, but they pretty much always get more complicated over time. So building in a test framework from the start is a sensible idea. Complicated procedural programs have the opposite problem, that they are at first glance not testable at all. But they can be made testable in very small steps using the island of happiness approach. Then the arguments against TDD moved from technical to financial. Developing using TDD needs twice as much code as traditional ABAP programming. So it's easy to say, this costs twice as much, so do not do it. However, in real life, cost savings, even in the short term, outweigh any extra costs quite dramatically. Once you've managed to defeat all the arguments against TDD, then what is the next step? I'd like to end this course with a call to action, which is, the next time you have a small change to try and make, try using TDD and create the test before changing the production code. The first time will be agony. But after a very short time indeed, the light bulb will go on and you'll wonder why in the world you ever did things any other way. So go ahead, try it. You won't be sorry.